Dewpoint temperature. Consider a moist, unsaturated air mass. It's moist because it contains water vapour, but it's unsaturated because it contains no liquid water. Under these conditions, the actual vapour pressure is less than the saturation vapour pressure, so E is less than ES. What this means is that the atmosphere contains less water vapour than it would if the evaporation rate and the condensation rate were equal, in which case the air would be saturated. Now diabatically cool the air isobarically. Diabatically means that the air parcel is allowed to exchange heat with its environment, and because it's cooling it means that it's losing heat. And isobarically means that the pressure is going to be constant. Both the vapour pressure and the dry atmosphere pressure, in other words the total pressure, will remain the same. As the temperature decreases, so the saturation vapour pressure decreases. And what this means is that as the temperature decreases, so the evaporation rate decreases. Eventually, the saturation vapour pressure will be equal to the actual vapour pressure, which means that we've decreased the evaporation rate until it's equal to the condensation rate, and therefore the air is now saturated. The final temperature, which the air parcel reaches where saturation occurs, is known as the dewpoint temperature, T subscript D, because dew forms at that temperature. Here's a plot showing vapour pressure in hectopascals on the y-axis versus temperature in degrees Celsius on the x-axis. So we're looking at a Clausius-Clapeyron curve. Initially, we have a parcel of air with a temperature here of 30 degrees at a vapour pressure of 20 hectopascals. We cool that parcel of air so that the evaporation rate decreases, and eventually once our parcel crosses onto the saturation vapour pressure curve, the parcel becomes saturated. So the saturation vapour pressure has decreased until it reaches the actual vapour pressure. This is a neurological diagram, and it shows you two temperature traces. The one on the right is the actual temperature, the normal temperature that we measure, and the one on the left is the dewpoint temperature. The dewpoint temperature, as we've seen, is a measure of the amount of moisture in the atmosphere, and the separation between the temperature profile and the dewpoint profile is often used as a diagnostic for the presence of cloud. We can illustrate the principle of dewpoint temperature a little further using the following illustration. Imagine you have 31 bottles of beer in a row, and each one is a degree warmer than the last one, so that they have temperatures in a sequence from 0 degrees Celsius to 30 degrees Celsius. The bottles will have water droplets if they're cold enough, so liquid water will condense on them, whereas the warm bottles will remain dry on the outside. Let the bottle at temperature A degrees Celsius be the warmest bottle on which water droplets form. The dewpoint temperature will satisfy the condition where the dewpoint temperature will be either equal to or greater than A, but less than A plus 1 degrees Celsius.